Welcome to The Explainer. Today, we're looking way past the surface of the world around us. We're going to venture deep into a microscopic realm that literally dictates everything, from the screen you're staring at right now to the chair you're sitting on. We are decoding the architecture of the invisible. I want you to think about this for a sec. What makes a diamond practically indestructible, but a pane of glass so fragile that a stray baseball can shatter it into a million pieces? Or, why does iron hold up massive skyscrapers while salt just dissolves in a bowl of hot soup? Well, the answer isn't magic. And actually, it's not even just about what elements they're made of. It's all about how those elements are packed together. Today, we're building an intuition for the physical paradoxes of everyday objects. And to do that, we're zooming all the way down to the atomic level. Here's a quick look at our roadmap for this explainer. We'll start with order versus atomic chaos, then we'll meet the unit cell, tackle this simple cubic puzzle, figure out how nature packs atoms tightly, and finally look at what happens beyond the perfect cube. Let's dive right in. All right, section 1, order versus atomic chaos, and why materials behave differently. So our first stop really looks at this fundamental battle happening inside every single solid object you touch. It's the battle between strict order and total atomic chaos. Basically, the physical world is split in two. Over on the crystalline side, think of it like a perfectly built brick wall. The atoms follow a strict repeating 3D pattern over super long distances. And because every single microscopic bond is exactly the same, they have this really sharp, sudden melting point. But then on the flip side, we have amorphous materials. Amorphous literally translates to without shape. Picture a completely chaotic, dumped pile of bricks. The atoms here are just randomly arranged, with only short-range local connections. Because these bonds vary so widely, there's no sharp melting point. They just kind of gradually get soft and gooey when you heat them up. Let's ground this in the real world for a second. The metals in your car, the salt you put on your food, the silicon semiconductors powering the phone in your pocket, those are all crystalline. They play by strict, unbreakable architectural rules. But what about that fragile glass window, or the plastic of a water bottle? Those are amorphous. That atomic chaos is exactly why glass shatters so easily, and why, when a glassblower heats it in a furnace, it softens into this bendable, glowing blob instead of just instantly turning into liquid. Moving on to section 2, meet the unit cell. These are the basic building blocks of crystals. Now, for the rest of our journey through this explainer, we're going to focus entirely on that highly ordered world of crystals, because to really grasp how materials get their strength, we have to meet their foundational 3D Lego blocks. The crucial concept here is something called the unit cell. Now, let's just build some intuition here, skip the complex math. A unit cell is simply a microscopic box. It's the absolute smallest base pattern of atoms that if you were to copy and paste it millions of times in every direction, kind of like a 3D wallpaper, it would build the entire solid object. If you understand the unit cell, you understand the whole material. That brings us to section 3, the simple cubic puzzle, or how loosely can we pack? Okay, here is our very first atomic puzzle. I want you to imagine atoms as perfectly spherical oranges. Our first packing attempt is what's called the simple cubic structure. Notice how an atom sits at each of the 8 corners of a perfectly square box. They're basically just barely touching each other along the outside edges. But take a really close look at that shape. If you arrange spheres like this, what happens to the inside of the box? I mean, picture just how much empty, wasted space is sitting right there in the dead center. Well, it turns out this arrangement is incredibly inefficient. In a simple cubic material, only about 52% of the available space is actually filled with atoms. A massive 48% of the unit cell is completely empty void. Honestly, it's like packing a huge shipping container but leaving half of it filled with absolutely nothing but air. And because this packing is just so loose and inefficient, nature generally hates it. Almost no real-world materials use this structure. In fact, out of all the elements, only polonium, which is this really rare, highly radioactive metal, is a lone wolf that actually crystallizes this way at room temperature. For everything else, it's just way too fragile for a universe that prefers stability. All right, section 4, packing atoms tightly. This is nature's efficiency upgrade. So if the simple cube is way too loose, how does nature fix it? Well, here is nature's first major upgrade, the body-centered cubic unit cell, or BCC for short. Notice what happened here. Nature essentially took that big, empty void from the previous structure and just shoved one extra whole atom right into the dead center of the box. Now, doing this does force the corner atoms to push out and separate just a little bit, but it completely transforms and drastically improves the structural integrity of the entire cell. Just by adding that one single central atom, our packing efficiency jumps all the way up to 68%. We've eliminated a huge chunk of that empty space.
This tighter, more interwoven fit is incredibly strong. In fact, it's the favored invisible architecture for some of our absolute toughest, hardest metals. We're talking iron, chromium, tungsten. Literally, the strength of the massive steel beams holding up our bridges relies on this exact microscopic arrangement.
But, nature doesn't stop there. What if we want to pack atoms as tightly as physically possible? Enter the face-centered cubic, or FCC structure. Think of a grocer meticulously stacking a huge pyramid of oranges. They don't just stack them directly on top of each other, right? They stagger them. They place the top orange right into the little dimple created by the oranges below it. That is exactly what's happening here. There's an atom nestled perfectly into the center of every single face of the cube. This staggering strategy creates what physicists actually call a close-packed arrangement, and it achieves a 74% packing efficiency. And here's a really fascinating fact for you. With perfect spheres, 74% is the absolute mathematical limit. Nature literally cannot pack atoms any tighter than this in a cubic box. Because it is so dense and smooth gliding, this specific structure gives us materials that are highly workable but still tightly bound, metals like gold, silver, copper, and aluminum. Finally, Section 5, Beyond the Perfect Cube. Or what happens when boxes get squished? Up until now, we've kind of been making a pretty big assumption, right? We've assumed that nature always builds its microscopic boxes with perfect, neat, 90-degree square corners. But what happens when things get a little weird? Consider what happens if we take one of our perfect little cubes, grab it by two opposite corners, and just stretch it or squish it. The sides are all still the exact same length, but the angles, they're no longer perfectly square. It leans. It's almost like a distorted reality. Bizarrely beautiful metals like bismuth and antimony use this slanted rhombohedral architecture, and that directly contributes to their really unique, brittle, and often stair-step-looking crystal formations in the real world. So let's pull all of this together. We've gone on this whole journey of packing efficiency without needing to memorize a single math equation. We started with the simple cubic, loose, fragile, half-empty, and largely abandoned by nature. Then we watched nature upgrade to the body-centered structure, dropping an atom right in the middle to forge the tough iron of our modern world. Then came the ultimate stacking puzzle, the face-centered structure, maxing out at that 74% efficiency limit to give us dense, workable metals like gold. And finally, we saw how squishing those boxes gives us eccentric crystals like bismuth. It's a pure, completely intuitive trend, from the fragile and loose to the tightly packed and robust. And that brings us to the end of our microscopic tour in this explainer. The world around you isn't just some random collection of matter. It's a meticulously stacked, highly ordered geometric puzzle. So, I'm going to leave you with this. The next time you pick up a heavy iron skillet, or hold a piece of gold jewelry, or even watch a piece of glass shatter, ask yourself, how tightly are those invisible atomic oranges packed? Thanks for exploring with me. Stay curious and keep looking deeper.